Deep beneath the icy plains of Antarctica, a slumbering giant is beginning to stir. Scientists have made a startling discovery. Vast reservoirs of methane hydrates locked away for millennia are showing signs of instability. This finding has sent ripples of concern through the scientific community, raising urgent questions about the potential consequences for our planet's climate. Methane, a potent greenhouse gas, is trapped within these icy cages, known as methane hydrates. These hydrates form under specific pressure and temperature conditions found in marine sediments and permafrost. The discovery of active methane plumes rising from the seabed near the Antarctic Peninsula has heightened fears that this trapped methane could be released into the atmosphere, exacerbating the already dire situation of climate change. The sheer volume of methane locked away in these hydrates is staggering. Scientists estimate that they contain more carbon than all other fossil fuel deposits combined. If even a small fraction of this methane were to escape, it could have catastrophic consequences for our planet's climate. This is not merely a distant threat. Evidence suggests that these hydrates are becoming increasingly unstable, raising the specter of a potentially catastrophic release in the not-so-distant future. Methane hydrates, often described as fire ice, are a unique and potent form of methane storage. They consist of methane molecules trapped within a crystalline lattice of water molecules, forming a substance that resembles ice but can ignite when brought to the surface. These hydrates form under high pressure and low temperatures, conditions found in abundance in the frigid depths surrounding Antarctica. The concern lies in the fact that methane is a far more potent greenhouse gas than carbon dioxide, trapping heat in the atmosphere at a rate over 20 times greater over a 100-year period. While carbon dioxide remains the primary driver of long-term climate change, methane's potency makes it a significant concern, particularly in the context of short-term warming. The potential for a sudden and massive release of methane from these hydrates is a frightening prospect. Such a release could trigger a runaway greenhouse effect, leading to rapid and catastrophic climate change. The consequences of such an event are difficult to overstate, potentially resulting in sea levels rising at an unprecedented rate, extreme weather events becoming more frequent and severe, and widespread disruption to ecosystems around the globe. The stability of methane hydrates is a delicate balancing act reliant on specific pressure and temperature conditions. Unfortunately, these conditions are being disrupted by a number of factors, both geological and climate-related, increasing the likelihood of methane release. Geologically, the movement of tectonic plates can create faults and fissures in the seabed, potentially destabilizing hydrate deposits. Additionally, the weight of glaciers and ice sheets can influence the pressure exerted on these deposits, leading to their destabilization. The ongoing melting of glaciers and ice sheets in a warming world further exacerbates this risk. Climate change itself is a major driver of hydrate instability. As ocean temperatures rise, the delicate balance that keeps methane hydrates stable is disrupted. Warmer water can penetrate the seabed, gradually melting the hydrates and releasing the trapped methane. This process, known as submarine permafrost degradation, is already underway in some parts of the Arctic and is a growing concern in Antarctica as well. The potential threat posed by methane hydrates in Antarctica demands immediate attention and action. While there is still much to learn about these deposits and the factors influencing their stability, the potential consequences of inaction are too great to ignore. First and foremost, we need to expand scientific monitoring programs to better understand the dynamics of methane hydrates in Antarctica. This includes monitoring methane concentrations in the ocean and atmosphere, as well as conducting research to map the location and extent of hydrate deposits. Secondly, we need to integrate the risks posed by methane hydrates into climate models and international climate assessments. This will provide a more accurate picture of the potential impacts of methane release and inform policy decisions. This information is crucial for policymakers to make informed decisions about climate change mitigation and adaptation strategies. Thirdly, we need to strengthen international agreements such as the Paris Agreement and the Antarctic Treaty System to address the threat of methane hydrates. This includes setting targets for reducing methane emissions and promoting research and development of technologies to mitigate methane release. International cooperation is key to addressing this global challenge. Finally, we must invest in mitigation strategies to address the risks posed by methane hydrates. This includes exploring technologies for capturing and storing methane released from these deposits, as well as developing methods for stabilizing hydrates in situ. While these technologies are still in their early stages, they offer a glimmer of hope in the face of this daunting challenge.